Here we're going to characterize covalent and ionic bonds. And in order to do this, we really need to start with a nice simple definition of what makes up a chemical bond. So let's start by saying that a bond is going to be what we call an electrostatic interaction between atoms. Now, if we want to break this down one step further, we need to understand what an electrostatic interaction is. And that just represents an attractive force between a positive and a negative charge. In chemistry, this is going to be the positive charge of the nucleus and the negative charge of the electrons. And within an atom, yes, there's absolutely going to be an electrostatic interaction between the nucleus and that atom's electrons. But if you introduce a second atom and bring it into close proximity with the first one, all of a sudden the electrons of the second atom are going to be attracted to the nucleus of the first. And that's going to form an electrostatic interaction between the atoms, which we classify as a chemical bond. So down here we see three different examples, and these are going to be broken apart into covalent, and then this one on the right is going to be ionic. And before we get started getting into the details of each, I want to make sure that we have a firm understanding of what these different types of bonds represent. And for each of them, there are two things that I want you to know. For a covalent bond, the first thing you should think of is shared electrons. And the second thing in introductory chemistry is going to be that covalent bonds are often associated with nonmetals. Now, there are some notable exceptions to this, but covalent bonds often exist between two nonmetals. Over here for ionic bonds, the main sort of buzz phrase for ionic bonds is going to be the transfer of electrons. And what you're going to see with ionic bonds is they are almost always going to be between a metal and a non-metal. And so from just sort of a first look at covalent and ionic bonds, this is the information that you really want to know and have memorized. But now let's get into the mechanism and explain why these bonds are different. Why do covalent bonds share electrons? Is that sharing always equal? And what does it mean when we say that an ionic bond actually transfers electrons? So we're going to start here on the bottom left with diatomic hydrogen, so H2. And if we take a look at a single hydrogen atom, we're going to see that it has a positively charged nucleus, and it's going to have a negatively charged electron. And there's definitely, like I said earlier, an electrostatic interaction between the nucleus and this negative charge. But as soon as I introduce a second hydrogen atom, and I'm going to draw it to look just like a mirror of the original one, all of a sudden, the negatively charged electron of the one on the left is attracted also to the positively charged proton in the nucleus on the right. And the same goes for the electron on my new hydrogen. So you see electrostatic interactions going both ways. And what that results in is the equal sharing of these electrons. And this is going to look something like this. Where everything is sort of happy and attracted all over the place. All right. And so that's going to be a chemical bond, and this is going to be a single bond. And when we draw Lewis structures, it's going to look a little bit more like that. But let's talk a little bit more about what happened here. Because the elements that went into this bond are the same, we're going to have what we call equal sharing of those electrons. And if we want to give this a better name, what we call it is a pure covalent bond. Now, you're going to see things get a little bit different here in the middle because now we're dealing with HCl. And in this case, the chlorine is going to have what we call a higher electron affinity. And what that means is that if it's put into proximity with other electrons, it's going to pull on those electrons a little bit stronger. So let's draw that same kind of diagram here, where we're going to have the H plus, the positively charged nucleus, and that one lone electron. But then chlorine over here on the right is also going to have a positively charged nucleus. In fact, it's going to have a lot more positive of a nucleus because it has more protons. But then it's going to have its 7 valence electrons, and this is all important to note, but the most important thing here that I want you to realize is that this chlorine right here wants electrons more. And what that's going to do is that's actually going to pull this electron closer and closer to this chlorine. And what that's going to result in is more electron density over here on the chlorine side and less electron density over here on the hydrogen side. And so if we kind of bottle this up and give it a definition, this is going to be unequal sharing. And that's going to be called a polar covalent bond. And what is the downstream effect of this? Well, when you pull electrons closer to the chlorine side of this bond, it's actually making that chlorine a little bit more negatively charged. And so what you see here on this diagram of the actual molecule, you see this lowercase delta negative. What that represents is a partial negative charge. And over here you see a partial positive on hydrogen. And so that is the result here. The unequal sharing isn't going to result in a full positive or a full negative, but it will result in a partial negative and a partial positive, which is very important for later on concepts in chemistry. So lastly, let's shift over to the ionic bonds. And here we have the transfer of electrons. So we want to talk about what in the world that is. So let's start by drawing out my sodium. And this is going to have, of course, a positively charged nucleus. And we're going to have a single electron out here because sodium only has one valence electron. And then we have our chlorine. It's going to have a positively charged nucleus. And it's going to have its full 7 electrons around it. Now in this case, it's going to look a lot like what we saw in this polar covalent bond. But in this case, when you mix a metal and a high electron affinity nonmetal, instead of just pulling that electron really tight to the chlorine, it's actually going to completely transfer. And so what is chlorine doing? It's actually stripping that electron clean off of the sodium. And so what you're going to end up with is a fully positive sodium ion and then a fully negative chlorine atom because we added an electron to the chlorine and removed an electron from sodium. And that's exactly how you form an anion, a negatively charged ion, and a cation, a positively charged ion. And so you're definitely still going to have an electrostatic interaction here. But now this is going to be a full ionic bond because it's between discrete or full negative and full positive charges.